Okay. Hello, everybody. Can you hear me? Can you see the screen?
Yeah, we can hear you and see you.
All right. Thank you. So today we are going to see an additional transducer that is capable to transduce temperature. And this transducer is called thermocouple. Thermocouple is a specific transducer that is mainly composed by two different metals, wirings. So what we got generally is that we have material one that is giving me so find out sort of effect, and this effect is called Seebeck effect, for which in a circuit like that, so in a closed loop, for by two different metals that are joined in two places that are called junction, and these two junctions are at different temperatures, then then an electrical current flows because of generation of an electromotive force. Electromotive force. Okay, this is the effect that is very well known as the Seebeck effect. Let me see. Grazie. So today we are going to go about thermocouple, that is a transducer for the use for the temperature measurement. It is mainly composed of two materials that are connected into 2 points, 2 locations. These locations are called junctions, and these junctions are placed at different temperature, T1 and T2. As a result, there will be an electromotive force, or there is an output tension, EU, when referring to, for example, the electrical circuit based on one material, the second material here in that example. In order to explain this effect, the thermocouple effect, we have to go back in time and refer to Volta, that was the first one that observed that, but more recently Seebeck, that posed the physical representation of this effect. And as I wrote there is a closed loop that is composed by 2 different metals, and if these 2 metals are joined together and the joints, as I said before, are placed at different temperature, then there will be an electrical flow. And this electrical flow is capable to create what I call the output tension of the electromotive force. Okay, this effect actually could be explained by referring to 2 other people. So by referring to other 2 effects, these effects are the Peltier and Thomson effect. So the effect, the Seebeck's effect, could be explained as a result of 2 other effects. Okay, and these are the Peltier effect and the Thomson effect. By the way, Peltier effect referred back to 1834. Peltier was a French scientist, whereas Thomson some years later, 1851, and he was a UK scientist. Okay, just because we are here, Seebeck was a part of German scientist. Okay, so that we have all the nations. Yeah. So what is the Peltier effect? So as a first explanation of this thermocouple effect of the Seebeck effect, what we are saying in Peltier effect is that if there is, so let me talk about this one. If we are having a heating or a cooling at the junction of 2 different materials, is because there is an electrical current flow. So what we can say is that the presence of heating or cooling at a junction of 2 different materials, okay, is due when there is an electrical current. So the effect could be seen that what observed Peltier was that when a current is made to flow through a junction, heat may be generated or removed at the junction. So the Peltier effect mainly refers to the junction between two materials. Within these two materials, there is an electrical current that is flowing. Okay, because of that, there is a heat that could be generated through this junction or removed according to the sign of the current that is flowing. Okay, indeed, what we are having is that if dot Q is the heat flow through the junction, Mr. Peltier proved that this heat flow could be represented as pi 1 negative pi 2 times I.
If your board isn't updating,
Say it again, please.
your board isn't updating.
Okay. Okay. So what we got here is the heat flux through the junction. The pi's coefficients here are the Peltier coefficients. Of course, they are referring to materials 1 and 2, and I is the electrical current. Okay. And this equation is trying to mimic what's happening in reality when testing these two materials network connected to a junction and with electrical current flowing in it. However, this effect, when counting, just balancing the heat, this effect is not taking into account the heat due to the Joule effect and also to the thermal gradient that could be there. Okay, so although this equation could be considered a good one where representing the heat flow through the junction, this is a very limit. The validity of this equation is very limited because it doesn't take into account Joule effect and the gradient. So let me write that. So heat due to the Joule effect and the thermal gradient. Okay, so it's a partial vision of what's happening in a thermocouple. Then comes Mr. Thomson, okay, that discovered what we call now Thomson's effect. Remember the previous one here. is called Peltier effect. Okay. So we're referring to Thomson effect. Mr. Thomson, taking into account the outcomes of the Peltier effect, found out that the output tension, the differential potential, the electromotive force that could be measured should be dependent on the temperature, the change of temperature, temperature between the two junctions. Okay, so according to Peltier's effect, it should be that the output tension, the electromotive force, okay, let me call that in this way, should be a linear function of the difference in the temperature, delta T. Okay, so this delta T is, of course, to be considered between junctions. Okay, but because it was the finding of Mr. Thomson, but because both pi1, remember the Peltier coefficient, and of course pi2, so the coefficients, are not constant with respect to both the temperature and space, that is a different location of the material where we can test the temperature. Okay, this equation, the previous equation, is not experimentally validated, not in full at least. Okay, because we have to take into account these two other effects. Okay, so, and that is the actual Thomson effect. We can say he found out, say Thomson found out, that when a current, electrical current, is made to flow through homogeneous electrical conductor, heat may be generated if there is a temperature gradient in the conductor. Okay, and that is what is generally referred to as the Thomson effect. Okay, so in order to explain the thermocouple that is going back to the very beginning. Here we have this electrical circuit composed by two materials, 1 and 2, two junctions, different temperatures. Okay, we have an electrical flow, we have an output tension, EU, and the thermocouple effect, the Seebeck, or also called Seebeck's effect, is stating us that in a closed loop formed by two different metals joined in the two places at different temperatures, an electrical current flows, okay, thus generating what we call the electromotive force. Okay, in order to explain that, two other effects must be considered, Peltier's and Thomson. The first one refers to the junction. The second one, Thomson, refers to the conductor itself. The first one, Peltier 1, is saying that if there is an electrical current into a junction, then there could be a heat. It could be generated or removed. So it is a thermodynamically reversible effect. Okay, but this effect could not be used to explain the thermocouple effect because it doesn't take into account any temperature gradient nor the Joule effect. Now, putting aside the Joule effect that we know very well how to couple with that, in order to introduce the, in order to justify the Seebeck's effect, then we have to introduce the Thomson effect that is referring to the gradient that is occurring, possibly occurring, gradient, temperature gradient, of course, that is possibly occurring into the conductor. So if there is a temperature gradient, then there could be an electrical, there could be an heat flow if there is an electrical current. So putting these things together, the flow, the heat generated or removed by the Thomson and Peltier effect, we have the overall balance, the heat balance that we were expecting by referring to the Seebeck effect. Okay, that's the reason why we have to introduce these two effects, Peltier and Thomson, in order to justify the Seebeck effect, that is our thermocouple. Okay, so that is the basic that you should know when referring, in terms of principle, working principle, when referring to thermocouples. Now, let's see how we can use thermocouples, because I don't know if you're aware about that, but thermocouples are the most useful and used transducer in the aerospace field, but not only there, to measure temperature. So we need to consider carefully how is the working principle of this thermocouple and see what are the basic issues that are affecting such a kind of measurements. The first one, better. In order to do that, we have to introduce two laws, okay, that all thermocouples are complying with, okay. These two laws are called, the first one is the law of intermediate material. The second one is the law of the successive intermediate temperature. Okay, now let's see the first one, that is called the law of intermediate material. What does it mean then? Let's assume to have the previous thermocouple layout, but with a slight difference that I'm going to tell you. So let's have, just to remember the colors, okay, green and red. Let's have the I can't hear you. Say again. Yeah, sure, you have to know that, because with these laws you can apply thermocouple in real life. So
Can you repeat her question?
Say again, sorry.
Can you just repeat her question? Because we can't hear.
The question is, do you have to know these two laws? The answer is yes, of course, because thanks to these laws, you can use in real life those type of transducer thermocouples. Okay, so
Thank you.
low or intermediate material, we have material number 1, like that. Then we have material number 2. And then I just put in a third material like this. So we have material number 1, we have material number 2, okay, and we have the output tension. Then we have material number 3 over there. Okay. Let's assume that the operating temperatures are T2 as the one before. Then we got T1 and T1 prime. Okay. Now the low or intermediate material is saying me that by inserting any type of material into a thermocouple circuit, like the one that I've just drawn, has no effect on the output, okay, EU for our analysis, as long as both ends of this third material are the same temperature. Okay, or we can say or isothermal condition. Okay, so going back to our representation of the circuit, we have material 1 and 2, so the output tension will be the same as before if T1 prime and T1 are all the same and equal to T1, of course, the previous T1. Okay, and that is very important because, as you can figure out, we can have a number of different intermediate connections provided by a number of different intermediate materials that are not affecting at all our output tension. So our meter could be considered as truly representative of the temperatures, okay, that we are considering. Now, and that is the first law. Second law of successive or intermediate temperatures. This kind of law is referring to the same thermocouple circuit as the basic one, the first one. So we are having the first material, the second material, G1, G2, material 2, oh sorry, material 1, okay. Now, this law, the law of intermediate temperature, or successive temperature, is telling me that if we are having the joints at T1 and T2, so that we have an output tension E1, let me call that E output there. And now, if we set the same thermocouple to a different temperature, for example, T2 and T3, so that the output tension is, for example, E2, then if we set these thermocouple junctions at a temperature T1 and T3, it happened that the output tension, the corresponding output tension E3, will be equal to E1 plus E2. Okay? So once again, consider the thermocouple here, and we set the thermocouple to two different temperatures. Okay, the two junctions are two different temperatures. Let me say T1 and T2. Then we use the same thermocouple with a different temperature. Okay, T2 and T3, for example. Then, if we sum up the output tensions corresponding to these two different configurations, this output tension will be equal to the sum of the output tensions that we could have, okay, when referring to the same thermocouple, but this time having the junction at temperature T1 and T3. Okay, and that is what we call the law of intermediate or successive temperatures. Yes, instead of having T1 and T2 just on the drawing, we are just in T2 and T3. Okay, these two configurations will have E1 and E2. Okay, now if you use the same thermocouple, but now with the junctions at temperature T1 and T3, the output tension is the sum of the previous two. Okay, so E3 is equal to E1 plus E2. Okay. Now, how can we operate now this thermocouple? Okay, so what it's doing in real life is that first, so I just redraw the thermocouple, material 1, material 2, T1 and T2. So in order to operate those thermocouple, what you have to do as a first step is set one temperature junction at one reference value. Okay, for example, T1 is set to a very well-known value, the reference one. Then T2, that is the temperature of the other junction, is the unknown one. Okay, for example, we can provide a contact between the T2 junction with the actual temperature, okay? Or more generally, the other junction should be in thermal balance with respect to the environment that we would like to know the temperature, okay? The corresponding output will be, of course, referring to the output tension that is referring to both T1 and T2. But because T1 is a known temperature, the only unknown is T2. Okay? Just to be sure, this one temperature is also called as cold temperature junction. T2 is hot junction. Okay, so you can skip the temperature, so cold and hot junction. Because the cold one is the one that is the reference, okay? The other is the unknown, the hot. Okay, how can we set the cold junction, the temperature of the cold junction? For example, we can use your container in which there is, for example, melting ice plus distilled water. And that, of course, that condition guarantees 0 degrees Celsius. Okay, so we perfectly know what is the temperature of the cold junction, and that it is 0 degrees. Okay. Generally, what we can say is that in order to record both the Peltier and Thomson, that is the Seebeck effect, what we can say is that the output tension, EU, is a nonlinear function of such temperatures, okay? So it is equal to AT plus BT square plus C cubed for a given cold temperature, okay? Remember, we are setting one temperature to a reference value. And these ABCs, constants here, are material dependent, okay, and also temperature range dependent. Okay, so it depends on how the thermocouple is made. That is, what are the two materials that we are going to use, and what is the temperature range that we are considering. Okay, according to different operating conditions, we can have that A, B, and C are all varying. Okay, the sensitivity of that S is the EU over T, okay, the output over the input once again. So in our analysis, just assuming that is valid the previous law, it is equal to this square. And the order of magnitude of this is about 10 microvolts over degrees Celsius. So it's very high sensitivity, okay? But of course, this value is a function of the temperature. Okay, as I said before. In order to characterize the different thermocouples from the material point of view, we give thermocouples some names. Okay, now I'm going to explain the names later on, but just to give you an idea of the sensitivity of such a thermocouples, what I can say is that the maximum sensitivity is for what we call T thermocouples, okay, evaluated at 350 degrees, that is about 60 microvolt per degree Celsius. Okay. About the minimum sensitivity is for thermocouple type S, okay, at 100 degrees Celsius, that is about 6 microvolts per degree Celsius. Okay, this is telling you what is the sensitivity range when using different thermocouples. But of course, this sensitivity not only depends on the material type that you are using, as T-type thermocouple, but also on the temperature range. Okay. Just to end this first part of the class, let me explain the meaning of the letters that I use in order to identify the thermocouples. So I can write this table, thermocouple type, and their usage in terms of the temperature range in degrees Celsius. So we have thermocouple type J, that is sort of steel alloy and Costantana, that is another alloy, and the temperature range is from negative 150 Celsius up to 750 degrees. Thermocouple type T, that is a copper alloy mainly based, and once again Costantana. And that goes from negative 250 degrees up to 340 degrees. Thermocouple type S, that is a sort of platinum and a composition of rhodium and platinum in negative. And the kind of thermocouple goes from 0 up to 1040, 480 degrees. There is the last one that we can consider, CR, that stands for chromel, and alumen. It's not aluminium, it's alumen. That goes from negative 270 up to 137 degrees. Okay. Please remember that this is chromel. And that is alumen. Okay, so different operating ranges in terms of temperature, different couplings, material couplings, that is different thermocouple types. Okay, and the way we are operating this thermocouple is that we have to set one junction at a known temperature, the other one at the unknown temperature. The cold junction, the hot junction. Okay, according to the different materials and temperature range, we have a variety of sensitivities. So it depends on the usage that I need to have in order to use the appropriate thermocouple. Okay. Okay, we can stop for a while, let's say 5 minutes, 10 minutes, and then we resume the class. resistance is there, but what we are measuring is the output tension. So it's sort of open circuit that we are preparing. No. There is no, I would say, bridge measuring circuit here. No resistance at all. Just two materials, and you just measure, as you can see here from the general layout. Yeah, okay. The output tension. So what you need to have, of course, is a very large resistance measuring circuit, as we already proved, in order not to modify the overall circuit. But just that. Are different, of course. If they are different, then there is an output tension. As long as the two junctions are in a, let's say, balanced condition from the thermal point of view, then the output tension is the one that you need in order to have the measured temperature. In the second part of the class, we will see how to estimate the temperature. For now, just keep in mind the working principle. Okay. So 10 minutes break. Hmm? Oh, no, thanks.